Good morning, good afternoon, everybody. Thank you for taking the time to join us today. My name's Guy Buttle. I'm the product marketing manager for the 3D scanning portfolio at Octon, the Geomagic portfolio. And today I'm joined by Joel Pollet, who is the product manager for 3D scanning solutions at one of our partners in the US, Cimquest. And today he's going to present a really interesting application of reverse engineering in the CAM space using Geomagic Design X Essentials. He's going to take you through a number of different workflows that can really utilize reverse engineering to save you time and get you from scan to NC faster than many other processes. A few bits of housekeeping before we get started. The presentation should last around 45 to 50 minutes to leave us with 10 minutes at the end for a Q&A. If you have any questions as we run through this presentation, on the GoToWebinar control panel, there is a questions section. Feel free to drop your questions in there. I will be monitoring that as we go through, and we'll open up the floor to questions for Joel to share his knowledge at the end of the session. So without further ado, I'll pass over to you, Joel. Thank you for joining us.
Sounds great, Guy. Thank you so much, everybody, for joining. And as Guy said, this morning's webinar is going to be addressing a topic called From Scan to NC. We'll talk about reverse engineering for CAM applications. So my name is Joel Pollet. Let me get back to the main screen. I'm the product manager here at Cimquest for all of our scanning and scan processing technology. I also wanted to take just a minute to thank Steve Weber. Steve is actually one of our senior level Mastercam engineers, applications engineers, and all of the toolpath display that I'm going to be showing throughout my presentation was created by Steve. So I just wanted to give a quick thanks to Steve for taking care of that for us. So today's webinar is going to focus on deriving high quality scan data from high quality CAD data from scan data to then be used to produce CNC programming. Reverse engineering using manual gauges and measuring devices can generally be tedious and very time consuming. And for some complex parts, it can be virtually impossible. Additionally, many of the automated reverse engineering products do not produce acceptable models to be used in CNC programming. So today's webinar is going to show how Design X Essentials can produce CAM-ready models from either point clouds or from mesh data. So consider this. Have you ever needed to CNC program a part, but don't have a drawing or a CAD model? Do you have broken parts in need of replacing? Have you ever tried CNC program using a solid model that was auto-surfaced from a mesh? So if you've answered yes to any of these questions, I believe you're going to enjoy learning about Design X Essentials for NC. So just a quick review of the agenda for today. We'll go through a quick Cimquest overview. Then I'm going to do an overview of the Design X Essentials user interface to show how the screens work. Then we have 5 short exercises that progressively utilize more and more challenging mesh data, mesh as well as point cloud data, where we're going to take you from mesh to model to CNC toolpath. The first example is going to start out with a very basic prismatic mesh model that we'll take into modeling. We'll go through building in design intent, and we'll end up with good CNC code. Next, we'll go through a little more complex prismatic modeling, but we'll go again from scan into model and then into CNC programming. Then we're going to take a little detour from CNC and we're going to talk about fixture design. So I have the scan of an airfoil, and we're going to discuss how we can utilize the airfoil scan to build a riser block underneath the airfoil to support it for perhaps an inspection or a CNC programming application. Then we'll get back on track onto the CAM side, and we'll take a turbine blade scan model. We'll go through the reverse engineering process of that, and we'll go through a 4-axis toolpath for there. And then finally, we'll end with just a very, very complex mold cavity design that's actually a propeller blade mold for a helicopter propeller. And we'll go from taking that from a point cloud actually into a model and then ultimately into CNC toolpath. So a quick overview about Cimquest. So since 1990, Cimquest has been one of the nation's leading providers of best-in-class design, engineering, and manufacturing products. Our visionary CEO, who founded Cimquest, continues to lead our R&D team to review new technologies as they emerge and brings them in-house for testing and validation by our experts. Cimquest has roughly 70 employees and is headquartered in Branchburg, New Jersey, with several physical offices throughout the Mid-Atlantic and Northeastern states. We offer pre-sale support, custom demonstrations, training, installation, and ongoing technical support for all of the products that we represent. Our current product suite includes several 3D printers, including metal printers. We represent a product called the Universal CMM from Verisurf Corporation, which is actually metrology CMM software that resides inside of the Mastercam user interface, and it's used for CMM programming for either manual or automated coordinate measuring machines. We represent Cimco as a shop floor networking product, and Cimco also has shop floor data collection. Of course, we represent all of the Octon products for reverse engineering, inspection, mesh repair, and then freeform modeling. And then the goal of today's presentation is to focus on the Geomagic Design X Essentials product, and as it is going to be used to pass geometry into Mastercam. Regarding Mastercam, again, Cimquest has been in business since 1990. We've been a Mastercam reseller pretty much from the onset, and we historically have been one of the top resellers for Mastercam for sales, service, support, training, ongoing maintenance for the past 3 decades or so. So just a quick general overview of what is Design X Essentials, and right now I'm calling it Design X Essentials for NC. So this is actually a point cloud scan, and the reason I'm starting out with a point cloud scan and if you look at the lower left picture, it's a very sparse point cloud scan. So this was actually not developed from a scanner. This was taken by taking one of the portable arms with a Renishaw ruby tip on it and just literally dragging the probe over the surface. So this probing scan, if you will, was taken several years back. But my point here is we have very sparse data. When we look at that point cloud scan in the lower left, the data is extremely sparse, but yet we have enough power and enough intelligence in Design X Essentials to go from that scan to a fully functional step file, step or power solid model, where we can then develop nice clean toolpath from that. So what Design X Essentials for NC really is it's a bridge to go from either scan or point cloud data into fully usable, somewhat editable solid models, depending on the CAD and CAM technology where we end up. So continuing forward, let's go through a little bit of an overview of the user interface of Design X Essentials. So Design X Essentials looks very much like a CAD system where we have a graphic screen, we have a tool tab, and then we have a history tree on the left side. Now, when we look at the history tree, there are 2 products. There's Design X Essentials and there's Full Design X. I just wanted to take a quick mention that in the Full Design X product, we have the ability to take that complete history tree that would contain planes, sketches, constraints, dimensions, features, essentially complete models, and we're able to pass the complete model into CAD software. So then when those models would get opened up in CAD software, they would look as if they were created in that native CAD software. So that's not the purpose of today's efforts. Today, we're going to be showing Design X Essentials, where the same type of history tree is still created, but we use it here for editing and for making modifications to the file, but the ultimate exported file is actually going to be either a step or a power solid file. We have masking tools for turning different components on and off on the graphic screen. We have graphical mesh control tools across the top of the screen. And then we have some display properties on the left side of the screen. So next, what we do in DesignX Essentials is we utilize the mesh as a template, and we can extract all sorts of best fit data from it. And my workflow in this first simple example will demonstrate how this works, plus how we build manufacturing intelligence into the model, otherwise known as design intent. But I guess in our case, we should probably call this manufacturing intent, because what we're going to do is we're going to take this part and discuss how we make sure that when we create a solid model and we run an end mill around the outside of the solid model, we want to make sure we have tangency constraints in that outer profile. We have two pockets in this simple part. We have a closed pocket and an open pocket. So what we're going to be doing is creating best fit planes, selecting triangles on the floors of those scans to represent the pocket floors. We have a variable fillet radius. So DesignX Essentials has some advanced modeling features as well for creating features like that. We have a blind hole with a countersunk top that we'll talk about. And then we have a dome top here of a part. So we have kind of a dished top. It's a three-dimensional top surface. So our first exercise is going to take us through going from a mesh, building design intent into the sketches we create in that mesh, creating a solid model, ultimately exporting from that solid model out to a step file, and we'll bring that step file into Mastercam. And in this case, we're going to focus just on that one front pocket in Mastercam, and we're going to discuss lots of different tools here. We'll go through capturing best fit features. We'll discuss something called mesh sketching, and we'll talk about building manufacturing design intent into the model. So if we switch over here, we now can look and we can see that our mesh is indeed a mesh. We turn the edges on for the triangle. So what we're going to do is go into our display tools for now, and we'll go ahead and turn the mesh display off. Most users don't like looking at the 3D mesh. With the tools on the left here, we have display tools to turn things like the mesh on and off, to turn the reference planes on and off. We can go into different views where we can change from top views. We can roll the views down, pan them around, flip them over. We have capabilities to select normal view, which is sometimes very important when we want to look down the spindle here at a toolpath. If we jump back to a top view and we zoom this down a little bit, the right side of the menu on top is our mesh selection tools. So here we have tools to do things like select triangles on the face. A lasso selection is a very popular type of a selection tool for mesh selection, so we can use that as well. So let's talk about how we go from here to a usable model. We're going to go ahead into our sketch tools, and we're going to mesh sketch starting from this base plane, and we're going to just position the plane where we can capture the outer boundaries of our mesh. So the pink curves, and I'm going to go ahead and turn the mesh off so we can see them more clearly. The pink curves represent what are called polycurves or poly edges. And what we can do now is we can best fit actual arcs on top of that geometry. So again, we're taking advantage of where that plane sliced through the mesh. And we're going to go ahead and create those arcs. Next thing we'll do is we'll add a line, and you'll notice we're in a sketching tool right now where we can go ahead and sketch geometry, very similar to a sketching tool that you might see in CAD. The next thing we're going to do is ensure that we have tangency, because if we run an end mill around the outside of this profile, we want to make sure we have tangency at all of the tangent endpoints. So we're going to go ahead and, regardless of whether or not these edges would be indeed tangent, we're going to build tangent constraints into every endpoint up here. And by doing this, we're then ensuring that we have tangent conditions at all of those endpoints. So then when we do run an end mill around the part, we know we'll have tangency. We'll just trim up these edges to get a fully enclosed model. Then we'll exit the trimming tool. We'll jump into our smart dimension tool and start building some more design intent into the model. So we'll place dimensions on the radii on the left side of the model here. And we'll place a dimension on this bottom fillet. And then we'll also go ahead and just add a quick dimension on the top shape here. And next we'll add some more design intent. We're going to take the radii on the right, and we're going to select the radii on the left and make sure that they're set equal. So we're going to set equal constraints. So again, we're building more and more intelligence into our sketch. So we know that when we ultimately build our solid model, we're going to have the tangencies we need. And here we're going to just dial in these numbers to being with fewer decimal places. So let's make that about a 3.5 inch dimension. And we'll make this about a 29.2 inch dimension. And keep in mind, changing these dimensions is also changing them on the opposing side. So at this point, we have a fully dimensioned, fully constrained sketch with our design intent built into it. The next thing we'd like to do is we'd like to take that sketch and extrude it up to the very top surface of the part. Unfortunately, the top surface of the part right now is still mesh data. So mesh data, as many of you are, I'm sure, familiar, is fairly dumb data. It's just a bunch of triangles. So we have the ability in both DesignX and in DesignX Essentials to create something called regions. You can think of a region almost as if it's a surface. And all I'm doing here is I'm using the polygon tool to drag my way around the model and just select triangular faces. And then ultimately, when I'm done here, just kind of finish this off. You don't need to select really all the triangles on top. You just need to grab enough of them that the software can go ahead and recognize that surface as a region. So now if we just turn this up on end and we take a look, we can see the region. We can see that it's a three-dimensional shape. So let's go ahead for now and just turn the mesh and the region off. And just going through some typical CAD type functions, we're going to take that 2D fully constrained profile, and let's select it. And let's go ahead and give it some thickness. So we can drag it up and down, or more appropriately here, we can go back to our mesh display tools and turn them on. And we can say we want to extrude that profile up to a region. So by clicking a region, we now have our first solid model, first solid component, I should say. If we come down and use our masking tools, we can turn the region and the mesh off. And if we now view this solid model in a top view, we can see that the radii on the opposing sides are the same. We know we have good tangency going from edge to edge. So we know we're kind of in good shape. Let's also go through and add some planes to the bottoms of those pockets. And we're going to use a rectangular selection tool now. And we're going to select the triangles on the bottom floor of that plane. And we'll best fit that plane through those triangles. So plane 1 is best fit through the enclosed pocket. And now the open pocket, we're going to go ahead and select triangles on that floor, but then we'll remove the triangles around the hole. And we'll select that as plane 2. So going up into an isometric view here, we can see that plane 1 and plane 2 are going to be the planes that we select for our next mesh sketch. If we turn the model on and we turn it back off, we can kind of see where everything is situated. So here, if we move forward and we step our way through the balance of the model creation, we can see our mesh sketch down at the very bottom of that open pocket. If I proceed forward, we get a little bit clearer view with the mesh turned off and the solid model turned on as to what that mesh sketch looks like. So again, going back to the mesh, we can see that the profile is defined at that plane, plane 2, and we have the 2 lines in the arcs, and we have the tangency constraints built in, and we also extended that pocket to go a little bit outside because we're going to cut away that shape. And ultimately, when we pass this into Mastercam, that's the pocket we're going to focus on. So as we step forward, we go to an extrude tool where we take that profile and we extrude it up through the solid model. We create our first cutout. Similarly, we create a mesh sketch at plane 1. And we go through a similar exercise at every corner. We want to make sure we have tangency constraints. So if we were to run an end mill around that profile, we end up with Geo1 and Geo2 motion. So here we have the nice tangency constraints built in. And once again, if we extrude that up and cut it, we have our second pocket. Stepping our way through features, DesignX Essentials does have variable fillet radius capabilities. And in this case, the mesh has a fillet that goes from an 1/8 inch up to a 1/4, wraps around the radius of a 1/4, and then reduces back down to an 1/8 inch. So our software is capable of handling variable radius fillets if they exist on the mesh. Stepping forward, we also have face fillet capabilities. So again, a common filleting tool used in CAD software. We want to take that purple face on top and we want to generate an 1/8 radius as it runs around, hitting all the green fillets. So we can see the slight orange geometry representing the 1/8 fillet running around those intersections. And then the last feature in the part that we're going to create is this countersunk hole. So we're going to go ahead and create the whole feature. In this case, we created a circle by passing plane 2 through the mesh. We extruded that circle in the upward direction, going through all, but then in the downward direction, we just went down to the blind floor on that pocket floor. So we have our blind hole defined, and the very last feature here is a chamfer. So if we just step forward and we turn the mesh on, we can see that when the mesh is on and when the mesh is off, there's a little bit of CAD bleeding through, but we can still see we have some pretty good detail here showing up. One thing I want to point out here is when we build a CAD model, we're creating a model with perfect dimensions, right? So the CAD model is absolutely perfect, but when you scan parts, you're somewhat you're limited in a few ways. Number one, the part that you're scanning has been manufactured, so it's not perfect geometry. Number two, the parts are generally worn, so they're even less perfect. And then number three, your scanner most probably has a little bit of error built into it. So your scan data, and then as you reverse engineering data, one of the reasons you can apply driving dimensions to the model is you can go ahead and set dimensions to be the correct dimensions, meaning you can go ahead and take dimensions and if something says it's a 0.998 diameter, you can go in and force and say, no, that's actually supposed to be a 1-inch diameter. So as we step forward and we go into Mastercam, we can then go ahead and take a quick look at the toolpath. Now we're not going to show the toolpaths for the complete model, but out of DesignX, what we did was we exported a step file. We imported the step file into Mastercam. Again, those of you that have machine parts coming directly from scan data, you know how that looks. But here, because we built the constraints into the model, you could see very nice, smooth, continuous toolpaths. When we post this out, we're going to be able to see, nice Geo3 motion as we wrap around those radii. Let's go ahead and Mastercam and just post out just the one toolpath. Again, we don't want to post the entire job because it'll take a little bit too long. So we'll post just the one toolpath. So Mastercam is jumping into Code Expert. And again, this is where the rubber meets the road, right? So when you take a look at this G-code file, it doesn't look like it originated from scan data, right? It originated from good quality CAD data, where you see Geo1s for the linear moves, you see arc moves, back to pocketing moves, and so on and so forth. So very, very clean transition going from just a very basic part scan going into the model and then building design intent and manufacturing intent into that model to make sure that the subsequent tool motion is what we want to see. Stepping into our second exercise, we're going to stick with a prismatic model for now, but two differences from this model. This is actually a gas valve, and the differences from this this model to the previous model, number one, certainly there are many, many more features to model. But then this model also has some internal or underside features that will just quickly step you through the modeling there. And then from this model, we thought it would be interesting to show what's called the dynamic OptiRough toolpath. So when we take this into Mastercam, we'll generate a stepwise roughing routine that takes you from top to bottom, working again from roughing from the very top of the shape down to the bottom of the shape. So the modeling features in DesignX Essentials that we touch here are that weren't addressed in the very first presentation are the shell command. We're going to use a tool called Cut with Surface, and then we'll go through the modeling of the internal features. So here in DesignX Essentials, again, when we look at the mesh, we think to ourselves, well, how do we want to model this mesh? Again, very much like you would in a CAD system. So I started out with a cylindrical shape, and then I took a angled plane where that cylindrical shape ends, and I chopped away the top portion of that cylinder. And then I simply used the radius rather, on the mesh to go ahead and build the torus type shape wrapping around that feature. So from this point forward, I'm going to go ahead and turn the mesh off, and we'll flip the model over and we'll go through some more modeling techniques. So again, from here, as you can see on my left, I'm just stepping my way down the history tree. We have a shell command where we can go ahead and select a face to remove and provide a thin wall thickness. We add a flange to the top of the piece. Next, we add an extrusion that's going to extrude out, starting from one end of the valve and extruding out the other end. But in this particular case, we don't really want that whole long chunk in the middle. We just really want the two ends of this extrusion. So what we can do in Design X Essentials is we can define a surface representing the inside of that shape. And then we can go ahead in the software using something called a surface cut command, can let us go ahead and pick the surface bodies that we want to remain. So in our case, we want these bluish green bodies to remain. We want to get rid of the orange body. And then stepping forward, the software is able to scoop that out for us. So continuing forward, we have some simple basic extrusions that we've added to the outside of this valve. And then we added these internal features, which are really very basic cylindrical rotation features and holes. We've flipped the model over, and we'll go ahead and add that boss base, I should say, up on the top of the piece. We take the base flange here of the cylinder, and we're filleting those radii. Then we're going to add some tooling tabs on the tops, and then we're going to add some tooling holes that are going to mount this gas fixture down. And while we do all this, we can make sure the holes, the tabs, and the base plate all are concentric to each other. So again, we can model in our design intent, our manufacturing intent directly into the product. Finally, we end up with little tabs on the sides of the part. We pass this into Mastercam. And then in the Mastercam user interface, oops. Sorry about that. Get back there. There we go. Then in the Mastercam user interface, we can go through the processing of the toolpath. So again, we generate the OptiRough toolpath. Rather than showing this as just a back plot, we're going to go ahead and go into the solid simulation tools in Mastercam and show it as a solid simulated feature. So this toolpath could end up being either a 2-axis or a 3-axis cut, but primarily it's two-dimensional. So it's a roughing toolpath to just rough away materials. But my point here is if we didn't have a clean model to work with, we wouldn't have good clean toolpath that we can go ahead and create into the model. So let's go ahead and select that toolpath, and also let's go ahead and post that out. So we'll hit our check. We'll go ahead and rename test NC as we did before. We'll hit the accept key, and then we'll go ahead and just quickly take a look at the toolpath motion here. So jumping into Mastercam's Code Expert, we'll be able to see up on top that we do have some 3-axis motion, and then we have some 2-axis motion as we pan down through the model. So again, going from basically a mesh to a little bit more of a prismatic shape, and then into more of a complex 2- and 3-dimensional toolpath. The next feature we're going to talk about here, so as I mentioned, we're going to step away from the CAM world and just to talk a little bit about fixtures design. So in blue, we have the scan of an airfoil. And what we're going to talk about is just how would we go in and create, let's say, a base plate or a riser block that's going to support the underside of that mesh, but we're actually not going to design anything with the mesh. We're going to use the mesh to help to design this base plate. And we're going to introduce a concept that we call volume sketching. So here in Design X, if we say, let's create a mesh sketch on this plane, we can actually thicken the plane out to a volume. And then wherever that volume passes through our part, we can pick up the silhouette edges of the part and volume intersection. So here, I'm most interested in picking up the edges of the blade which I do have from that volume. So we're going to go into our sketcher. We'll turn the mesh off so we can get a good clear look at our polycurves. We'll go into the line function, and then we'll go ahead and best fit lines in each of these polycurves. Then we'll go ahead and draw some lines. So this is the first time we're actually just freehand sketching some geometry. And again, those in the audience who have worked with CAD modelers and sketchers, you'll notice the sketching tools here are not only virtually identical, they are identical. It's the same exact constraint solving tools, the same exact sketchers that you would see in a product like SolidWorks or Solid Edge and so forth. So let's go into our smart dimensioning tool, and we'll add a dimension just from that top line going down to this bottom line. And let's exit the smart dimensioning tool, and let's go ahead and just give this a value. We're going to say, let's make this 3/4 of an inch, and then we'll exit the sketcher. Then we'll go ahead and turn our mesh back on so we can see what's going on. So we have our rectangular base, and if we flip the part over, and we just kind of tip this back a little bit, we see we have a rectangle that's off in that plane, but it's a distance away from our mesh. Now, once again, the mesh is just dumb geometry, so we can't really extrude that rectangle up to the mesh. So this time we'll use the rectangle selection, and we'll go ahead and create an auto surface, or a region rather, down in the underside of that airfoil. Let's just turn the plane off here for clarity. So we'll come over and just shut off the plane, the display of the plane. And then we'll go through, again, from a modeling perspective, we'll take our 2D profile and we'll go ahead and extrude it up towards the airfoil. So we're going to say extrude up to a region. We'll select our region, and then the software builds that plate for us. And I didn't want to go into too much detail here. I wanted to really mostly show that for creation of things like riser blocks or base plates, you have the full gamut of a solid modeling product here as well. So you not only have excellent tools to convert mesh into solid models or surface models, but you also have tools to create brand new solid bodies from scratch. So stepping forward here, now we're going to talk about taking a turbine blade scan, and we're going to use the Blade Expert toolpaths in Mastercam for machining. So here we're getting into more involved data, obviously. When we look at the scan, we notice a few things about it. We notice those orange patches are actually holes or defective areas in the scan. When we're scanning for reverse engineering, and we have something like a turbine blade where we have blades that are in a repeated pattern, we really don't necessarily need to scan the entire turbine. We can really just scan a handful of blades here. So all I really cared about was having a few blades that had good scan quality that I can use for reverse engineering. So here we're going to go through the steps of how we go from the mesh of that turbine blade onto a solid model. And then we're going to use, again, Steve used a toolpath technique called the Blade Expert to go ahead and develop the 4-axis tool motion here in Mastercam. So the Design X Essentials tools that we'll be using here that are new are the Revolve Shapes, Lofts, Solidify, which is an interesting tool. We'll go through creation of circular patterns. And finally, the end result is we're going to machine some complex fillets, which are those sort of dark blue purple fillets where each of the blades meets the very bottom of the part here. So just to continue forward, let's go into the model of this propeller, or turbine rather, and we're going to roll the model back to the very first scan, and we're going to go into that sketch. So let's go ahead and go into that sketch. And the first thing we notice is there is some design intent already modeled in there, but let's go ahead and add some more. So let's add a vertical dimension here. We'll go ahead and add some radial dimensions. And again, we can kind of add whatever kinds of design intent, manufacturing intent we want to build in. We're able to go ahead and build into that 2D profile. Taking that profile now and revolving it, so we have our base hub to make the impeller. The next thing I did was I created a bunch of planes that were parallel to each other at an offset distance, working my way down one of the blades. And then I created a lofted surface passing through all of those cross sections. So those cross sections are simply planes slicing through the mesh, and then using the software to go ahead and create that lofted shape. Here you can see that lofted shape sits on the inside of that blade very nicely. So I took that same approach for modeling the opposite side of that blade. Certainly, we could have taken this blade and just simply offset it for thickness, or even on the mesh side, we could have thickened it into a blade for thickness. But I thought it would be more interesting to actually model the second blade, and it's a little bit harder to see the mesh inside those two oversized blades right now. The next thing we're going to do is create a cap. This is actually just a surface shape, and we're going to use that surface shape to cap off the top of the blades. So at this point, we have a cap for the top, we have a hub for the bottom, and we have the two blade shapes. So we're going to go ahead and right click here, and we're going to trim all of those surfaces down, and let's turn off all of this sketch geometry so we can just get a good clean look at the surface. So right now that blade shape is fully enclosed by the blue outside shape, by the hub, and then of course the two blades themselves. So when we take a look at this now, as we go down in the history tree, we have a modeling tool called Solidify. And if we say Solidify, the software can then take a surface model that's fully enclosed, and it can create a solid body from it. So we now take that solid body, and we're going to go ahead and create a circular pattern of 16 blades. If we go into that circular blade modeling tool, just so you can see how this works, just like any other CAD system, we can change the number of iterations here from 8 to 12, however many blades we want to have or we need to have, we can set. I'm just going to hit a Control Z just to undo that function and get back to our 16 blade model. So from this point, we need to address the underside of this blade as well, this turbine. So let's go ahead and start backplaying the axis of this turbine. So if we go to the bottom side of the model, we have the beginnings of the shaft there on the bottom. We have a concentric hole going through the bottom, and then we have some additional concentric holes. And again, that concentricity is getting modeled into the design to ensure that we end up with good, clean geometry for CAM. So here, if we just jump to the very end of the model, we're asking the system now to go ahead and place those complex fillets down at the hub level where all of the blades are meeting the hub. And we now see the fillets. We're going to go in first, before we compare this to the mesh, let's go in and just take all the sketches and turn them off. Just so we're only looking at solid data at this point. So here's a solid model of our complete shape. And if we come down and we turn the mesh on, again, we get a decent amount of overlap. The blades look good. The hub on bottom looks good. So everything looks like it's going to be in pretty good shape to go ahead and move forward into our toolpath capability. So when we come forward here into Mastercam, as always, and as with the previous shapes, we exported them as step and or parasolid. And here we're just creating a quick Blade Expert toolpath. Again, Steve built the machining of the entire model for us, but given we're limited by about 45, 50 minutes or so, I just decided to show just a single toolpath for each of these shapes. So we have our 4-axis cutting of the blades. If we now exit out of here, or I'm sorry, if we now go in and generate our G code for that machining, software jumps into Code Expert. And then here we have our nice clean 4-axis code where we have the X, Y, Z, and A data pretty much everywhere as we work our way down the part. So again, very clean geometry. The process is pretty much consistent. We go from the mesh, we pull information from the mesh, we build design intent into the CAD, whether it's a sketch or a mesh, and then we go out and create a model and machine the model. So our final model here is essentially stepping back to how I started out this presentation. We talked about having a very sparse point cloud that we started from simply by dragging a probe back and forth on the surface. And from that sparse point cloud, we're able to produce a fully functional, fully machinable step model where we create our toolpath from. So let's step forward into DesignX and take a look again at that tool motion. So just a reminder, look at how sparse the data is. Again, this was captured just by probing, not by scanning at all. Here, and again, just bouncing it around a little bit so you can get a good feeling that this isn't really the best quality data, but it was enough data for me to go ahead and model the top of that piece. So here, if we have the mesh and the solid model turned on together, we can kind of see what that looks like. What I'm going to do quickly, just so you can appreciate the surface integrity, is we'll turn off the edges of that cavity model, and we'll just twist the model around a little bit. There's actually 3 surfaces here that were created from that point cloud. And let's turn it kind of back around, and we'll go ahead and turn the edges of the model back on. So again, because we're limited a little bit in time, we don't really have time to go through the modeling of this part, but as I roll down this history tree, you'll notice there's a huge number of features, 3D sketches, trim surfaces, Boolean operations, all sorts of high-end, high-level CAD modeling tools to go ahead and create that shape. So again, a very, very detailed, very complex shape. And once again, we export that shape out into Mastercam. And we're going to go ahead and show the toolpath for that shape. So in Mastercam, let's go ahead and just backplot our scallop toolpath. And this is actually a roughing toolpath, although it takes the shape, so to speak, of a finishing toolpath. It's actually up above all 3 surfaces. But here we can see the clean, crisp 3-axis code, the entry points, the exit points. And as before, if we go out and we say, let's generate code, we'll accept the change in code name here, and we'll let the system process. Mastercam launches Code Expert. It's going to go ahead and display our 3-axis G-code file. So again, here, just scrolling from top to bottom, we can see our 3-dimensional tool motion all throughout the part here. So transitioning forward, and to summarize what we've gone through before, number one, we can utilize data using DesignX Essentials. We can then utilize data from really any scanner or any probing device. The caveat is we need to make sure that the accuracy and the resolution, which is also known as point spacing, are appropriate for the job. I always like to take a few minutes to just kind of describe the differences between accuracy and resolution, because this comes up a lot with customers and it's kind of a confusing point. When you scan a part, the accuracy of the scan data is how far away are those scan points from the surface that you're scanning. So pretty straightforward. If I'm scanning a part and my scanner has a plus or minus 20 micron accuracy, then the points that I create are within plus or minus 20 microns of that surface. Resolution, though, is a whole different story. Resolution is you can think of resolution as the density of the point cloud. A lot of scanner manufacturers refer to resolution as point spacing or point distance, but it's essentially how dense is the point cloud. So when you look at a part like this is a gap gauge from AutoZone, and obviously it's a very small part with very tiny features. We actually scan that with a scanner that has a 20 micron resolution. So 20 microns is about 8/10,000ths of an inch. So what that means is when you look at the scan that was produced on the right side, the density of the point cloud before that mesh was created, the points were never closer to each other than 8/10,000ths of an inch. But when you look at that scan, you can see the increments going around the perimeter. You can see those fairly clearly. So if we needed to make, let's say, a toolpath of an engraving toolpath in Mastercam or in CAM software that goes around the outsides there, we probably have enough geometry to do that. But if you look at the AutoZone logo and you look particularly at the letters Z and N in zone as compared to the actual part, you can see they're a little bit washed out. I always tell people anytime you look at a scan and it looks like the scan is melting, generally it means the point cloud was probably, the resolution was probably not quite high enough. So that's really the difference between resolution and accuracy. So if you're scanning things like car doors or big, large, swoopy shapes, resolution becomes much less important. When you have fine detailed parts, resolution is far more important. Next, DesignX Essentials provides CAD modeling tools identical to the most popular CAD systems. So again, those of you who have experienced working with products like SolidWorks, NX, Solid Edge, Inventor, you probably saw a lot of modeling tools that are virtually identical to what you're used to. The big difference here is we can bridge the gap between scan and CAD data and end up with very machinable models. We can build intelligence into the models to ensure things like tangencies and equal size, and making sure that our design, or what I call our manufacturing intent, is built into the model. You're able to overlay the desired surface or the derived solid or surface model with the original scan data that we can ensure shape integrity. The creation of a mathematically accurate step or power solid model from, in our case, very dumb data. And again, data doesn't get much dumber than just a bunch of points pulled from a probe dragging along a surface. So you can see that DesignX Essentials gave us enough tools to go from that very sparse point cloud out to a very sophisticated model. And while the emphasis of today's examples were on milling, I just wanted to point out that certainly if you have turning applications, router, laser, contour laser, EDM, punch press, it doesn't really matter. The software will work the same way. The final point I want to leave with everybody is we do a lot of live demonstrations and we utilize customers' parts when we do these demonstrations. So you can get a really good understanding how the technology works with your parts and just works in general. So at that point, what I'm going to do is turn things back over to Guy for any questions that might have come up.
Thank you, Joel. That was great. Super interesting workflows. It's great to see something a little bit different, and how DesignX Essentials can be used in these kinds of processes. We've got a couple of questions here to be getting on with. If you've thought of anything as you go through, make sure to drop them in the questions box here. We've got about 10 minutes left. The first one, I know you've spoken primarily about Mastercam for programming, but can this kind of workflow be used alongside other CAM tools as well?
Good question, and of course it can. As a Mastercam reseller, we have Mastercam at its to use in this particular case, but the same workflow that I showed today would really work with any CAM software. So it's not unique or specific to Mastercam. Cimquest is a large Mastercam reseller, and we have Mastercam from a demonstration perspective. But really, any CAM software would be usable.
Great. We've got a question here about automation. Is there any automation tools for contour region recognition for the point cloud?
None that I'm really aware of. That's a good question. There are when you build a region in the software, if features are specifically cylindrical or planar or conical or spherical, the region that you build, the software will recognize that region as that analytic shape. So in the case of the two shapes that I built regions in today, both of those shapes were freeform shapes, right? The underside of the airfoil and then the top of that very first part we started with. Those were sort of freeform shapes. But if those shapes happen to be analytic shapes, the region shape would be recognized as a cylinder or a sphere or a cone or whatever it happened to be. So I'm not sure if that completely answers the question, but we can pull some intelligence from the region information that DesignX Essentials can produce.
Great. We have one here about obviously the parts that we showed are all very traditional engineered parts. What about parts like sculptures or carvings? Is there a way of still utilizing this kind of workflow for those kinds of components?
So no, because generally speaking, the organic shapes don't really lend themselves to this type of workflow. So what you could do, you could bring an organic shape into Geomagic Design X Essentials, and you can essentially bypass all of the modeling tools and just use a tool we have called auto surfacing. You can go ahead and place in, which is a more traditional way of how a lot of these products work. So we could take a mesh of an organic shape and we can auto surface that and save that auto surface out to a step file, bring that step file into Mastercam or any CAM software and develop a 3-axis toolpath. So you could certainly do that, but the size and the step over and the resolution of the toolpath are going to be directly proportional to the resolution of that mesh, if that makes sense. So if you have a mesh of a human face, the higher the resolution that mesh was used to take, when you pass that into Geomagic Essentials, you're going to have a more tight, a denser toolpath when you machine something like that. So yes, we could machine organic parts, but you wouldn't go through a workflow like I showed today. It would be a little bit different workflow to get to that same type of a step file.
I guess a more traditional surface
Right.
workflow where
Right.
uh, take the surfaces that you're given
Right.
essentially.
Correct. And
Uh,
that's because organic shapes really don't have, they're not really made from prismatic shapes or mathematically definable shapes. So that's really all we have to work with. And as you said, Guy, that's more of a traditional workflow is to just simply auto surface the model.
I guess if you have sculptures or kind of more carved shapes that have prismatic elements to them, if those are more important and the machining operations were to be uh, focused around those, you would kind of use a workflow similar to this, but combine it with an auto surfacing workflow as well.
Correct. You'd probably use a little bit of a hybrid workflow, both to get the full organic shape, and then maybe the prismatic shape maybe happens to be a torus or a cylinder. So you could certainly model that in. You could trim things up and end up with a shape. So where the most, the majority of the toolpath would be 3-axis on the organic portions, it would probably end up also being 3-axis on that prismatic portion as well. But yeah, you could go through a workflow like that as well, a workflow like that.
Great. We have another one here. What are the challenges one might face when integrating this tool with 3D printing rather than CAM?
So to prep a model for 3D printing is actually much simpler than to do what we did. 3D printers generally only care about having a fully enclosed volumetric shape. So you could use Geomagic Essentials to import a scan. Then you can use tools in Geomagic Essentials to fill any holes and repair any deformities in the model. And then you can actually just save back out that prismatic part. I'm sorry, the polygonal file as an STL. You could just export it back out. So you can take a scan in from a scanner, bring it into Geomagic Essentials. All the 3D scanner generally cares about is that you have a scan that can form a volume, right? A fully enclosed scan. In fact, some scanners, processors can even close holes for you, but you could use Geomagic Design X Essentials also to prep models for scanning, where you're filling holes, trimming out bad scan, and then resaving out another polygonal file, another STL file, to then go to a 3D printer as opposed to going to a CNC machine or into CAM software.
Great. And a final question that we've got here, unless anyone else has any to drop in. What's the difference between Design X Essentials and Design X full version?
Yep. So the biggest difference, there are some subtle subtle differences in the two versions. DesignX is able to do something called a live transfer. So if you're, let's say, a SolidWorks user and you have DesignX, you can go through virtually an identical process that I went through today, but instead of exporting a step or a PowerSolid file, you can actually what we call live transfer that complete model into SolidWorks. So that would produce, in this case, an SLD PRT file for you if you had DesignX. And if you opened that SLD PRT file inside of SolidWorks, you would see planes and sketches and constraints and dimensions and features, and everything you use to model the part in DesignX would be passed into SolidWorks. So the DesignX workflow is a very similar workflow to DesignX Essentials. There were a few tools in that DesignX Essentials does not have, that DesignX does have, but the main tool is the ability to transfer the complete history tree. So if you needed to make further design edits to something that you reverse engineer and you're using a product like SolidWorks, then you would need the full DesignX product, and that would produce a completely editable native SolidWorks file for you. If you were using a modeler like something like SpaceClaim or Creo or something that has direct modeling capabilities, direct model editing capabilities, then something like DesignX Essentials would still probably work fine because those products can import Step and PowerSolid and make edits to them. So that's the major difference, though, is exporting a history tree in DesignX versus exporting Step or PowerSolid in Geomagic DesignX Essentials.
Perfect. I think that is all of the questions we've got today. If you think of anything else after the webinar, feel free to reach out to us on our website or directly to Joel. His contact information is on the screen now. I hope you found this useful. It's been a super interesting presentation from my point of view. Thank you very much for joining. Thank you, Joel, for presenting, and we look forward to seeing you on the next one.
Thank you very much. Thanks, everybody. Take care.